Hello, everyone. Welcome to the March 24th edition of Math 371, Intro to Linear Algebra. A couple reminders. There's actually no Pearson My Math Lab homework this week. Don't be too disappointed. But you still need to submit your notes online each day. So today is actually a pretty fun lecture. We're basically going to rehash some of the ideas we did before, but in the more general setting of vector spaces. So today we're going to talk about section 4.3. So we need to reintroduce the idea of linearly independent vectors. So it has the same definition as before. A set of vectors v1 up to vp is linearly independent if the only solution to this equation is the solution where C1 equals C2 equals CP is 0. So that's the definition of linearly independent vectors. And otherwise, we call the set linearly dependent. So a set's going to be linearly dependent if there is a solution to that vector equation where one of the coefficients or more are not equal to 0. So you've seen this before, and so a lot of it's very familiar. So quick remark, this set, if all you have is a single vector, is linearly independent if the vector is non-zero. So if I have a set of only one vector, that set of one vector is linearly independent if and only if the vector is not 0. Okay, so let's look at some vector spaces that you might not be as familiar with. Okay, so let's look at the vector space, what they call P sub 3. We're going to do P sub 2. These are polynomials with degree 2 or less. All right, and we're going to look at the following set: 1, t, and t squared plus 1. And I want you to pause the video and see if you can determine whether these polynomials are linearly independent or whether there's a linear dependency. So you're trying to solve the equation c1 times 1 plus c2 times t plus c3 times t squared plus 1 is the 0 polynomial. So pause the video and try to solve this. All right, now that you've tried to solve it, we can combine some of these terms. We see we have a c1, we have a c2 times t, we have a c3 times t squared, and we have a c3 here, and that's 0. So we see that c3 times t squared plus c2 times t plus C1 plus C3 equals 0. Well, if I look at this, I see there is a t squared piece on the left, but there is none on the right. And so that tells us that C3 must be 0. Similarly, we see that there is a linear term that is a term with t to the first power on the left, but none to the right. So that tells us that C2 equals 0. At that point, it's really not so hard to deduce that C1 must be equal to 0 as well. And so what this has told us is the only solution to the equation up here, the only solution is all zeros. So C1 is C2 is C3 is 0, which tells us that our set of vectors is linearly independent. All right. So let's look at another example. All right. So after I write this example, I want you to pause the video again and try to solve it. So we have 4 plus t, 2 minus t, and t. So I want you to pause the video and try to determine whether those are linearly independent or if that set of vectors is linearly dependent. All right, let's talk about the solution. One thing you'll notice is that if I do 4 plus t, so 1 times 4 plus t minus 2 times 2 minus t minus 3 times t, it equals 0. And so we have found a linear dependency. So what we see is that this set of vectors that I started with is actually linearly dependent. Because I was able to find a C1, a C2, and a C3 that I multiplied by these vectors, where it all added up to the 0 vector. So this is a little bit funny because we're thinking of polynomials as vectors, and you've probably not thought of them before. This 0 right here is actually the 0 vector in the polynomial world. Among polynomials. All right. Okay. So let's think of another example that I think is really interesting. And this is the example of continuous functions. So is the set of, excuse me, is the set of sine of x and cosine of x, is this a linearly independent set? Well, at first you might be thinking, there's no way for me to solve that. And in some ways, you're right, but here's one way to look at it. Let's suppose that there was some way to combine the sine of x plus the cosine of x and always get 0. This is always for all x. Okay, well, what would we notice? Well, if it works for all x, surely it will work for a couple x. So let's plug in some values. So this would tell us that c1 times the sine of 0 plus c2 times the cosine of 0 equals 0. Well, let's take a look. We know the sine of 0, that's 0, and the cosine of 0 is 1. So what this would tell us is that c2 times 1 is 0. Okay, c2 must be 0. Well, what other value can we plug in? Well, let's plug in the value of pi over 2. this must also equal 0. Well, we know that sine of pi over 2 is 1, and cosine pi over 2 is 0, and this will tell us that C1 times 1 equals 0. So C1 is also 0, and therefore what we can conclude is that the sine and cosine are linearly independent. For those of you who are in differential equations, you might see the Fourier expansion soon, and you'll see that more than just the sine and the cosine are linearly independent. Much more is true. Okay, so this is an example where we had functions as vectors, and we show that there's no way to linearly combine them and get 0. So let's go on to talking about what a basis is in this world. So a basis will mean exactly the same thing that it did before, but let's give the definition. You can write it down already if you think you know what it is. So let's let H be a subspace of V, which is a vector space. Remember, at some point, we identified all the criterion for being a subspace. And a set, which we're going to call beta, is a basis for H if all of these B's, if all the vectors B1 through BP, they all actually have to be in the subspace H, and two other conditions have to be true. Our set beta is linearly independent. And secondly, H has to equal the span of beta. So span, your favorite concept, just means all possible linear combinations. Okay, so just to see how your memory about these things is, I want to ask you a question. So, are the columns of an invertible n by n matrix a basis for Rn? All right, pause the video and answer yes or no. All right, now you've had the chance to do that. The answer is yes, they are. You can row reduce and you get a pivot in every row. What about the rows? Are the rows of your matrix a basis for Rn? Pause the video and see what you think. Again, the answer is yes, for the same reasons. You can row reduce, and there's a pivot in every column and every row. All right, so another reminder. Sometimes we look at special bases, and just a reminder, the standard basis is a very special basis. It's your favorite one. The standard basis for Rn is given by these vectors. So we have the vector E1, that's the vector we have 1, 0, and all zeros. We have the vector E2, which is the vector 0, 1, 0, 0, all zeros. and then you have the vector En. So this is not the only basis for Rn, but it is most people's favorite basis for Rn. Okay? And there's another vector space that we've been dealing with, Pn, which is the polynomials of degree n or less. And the standard basis for this vector space, basis for this vector space, is the following. We have the function that's just the constant function 1. We have t, or x, the linear one. We have the quadratic, the cubic, and t to the n. So this is a basis, and it's actually the standard basis for p to the n. Okay. So we've seen a lot of bases, and so now it's time for what's called the spanning set theorem. So the spanning set theorem, we'll talk about in a second, but one thing you should know is a basis is, in theory, the smallest possible set that can span a subspace H. Okay, so let's take a look at what an example of finding such a basis is. Okay, so we have 3 vectors, and we have the vectors v1, v2, (3, -1, and 4), and v3 is (-1, 5, and 6). Okay, so we're going to let H equal the span of these vectors. Okay, the span of these vectors. So the question is this a basis? Well, how do you check if it's a basis? Well, you can set up a matrix and you can row reduce. So let's do that. 1, 2, -1, 3, -1, 4, -1, 5, 6. Okay, so if we row reduce this, we can get 1, 3, -1, 0, -7, 7, and then we add that one, 0, 7. Oh, my bad. I forgot this minus sign right here, and right here. And then you can row reduce this a little further to this, and then just a little bit further to 1, 3, -1, 0, 1, -1, 0, 0, 0, and then 1, 0. Let's see, we subtract 3, so it should be a 2, 0, 1, -1, 0, 0, 0. Okay, so what is this telling us? It's telling us that the third vector, v3, is actually equal to 2 times the first vector minus the second vector. So what do you think this tells us about the span of v1, v2, and v3? Well, what it tells us is this is actually just equal to the same thing as the span of v1 and v2. Why is that? Well, we see that v3 is some expression of v1 and v2. So let's say that I have a vector that is equal to some combination of these three vectors. Well, what I see from my equation right up here is that this is the same as c1 times v1 plus c2 times v2 plus c3 times 2v1 minus v2. And so what I see is that any vector I can produce with v1, v2, v3 can be written as a combination of just v1s and v2s. And so what that actually tells me is I didn't actually need v3 to span H. I could just use v1 and v2. So what is this telling us? It's telling us that I can get rid of vectors, keep the same span, and then get a basis. So what happened was this is not a basis because we showed that v1, v2, and v3 are not linearly independent. They are in fact linearly dependent. But if I just look at v1 and v2, they are linearly independent, and you can check that by row reducing. And so what this tells you is that if you have a set that spans, you can reduce it until you get a basis. So that's what's called the spanning set theorem. Spanning set theorem. So what it does is it says we let S equal some collection of vectors. Let's call them V1 through VP. And H is going to equal the span of S. Now S might not be a basis yet because S might not be linearly independent. So if one of the vectors VK and S, let me make that a little neater, is a linear combination of the remaining vectors in S, then the set formed by removing the vector VK still spans H. And then what we should also know is that if H is not the zero subspace, then some subset of S is a basis for H. So what this is telling you is if I have a bunch of vectors and they span something H, maybe it's a line, a plane, a hyperplane, then some subset of those initial vectors must be a basis. Basically, this spanning set theorem is telling me I can throw away vectors until I get down to a basis. All right, excellent. So that's a good thing to know. And the proof, I think, is pretty self-explanatory why it works. All right. So now we're going to go back to looking at the bases for the null space of a matrix and the column space of a matrix. And you've done work with this before, but it's always good to revisit these ideas now that you have a better understanding of the vector space involved. So I want you to pause the video after I write in this example and find a basis for column space of A where A equals 1, 0, 3, 0, 1, -2, -3, 5, 1, sorry, -5 here, and 2, -4, sorry, -2, here we go, let me get rid of that negative sign. All right, so go ahead and see if you can come up with a basis for the column space of the matrix. So pause the video and give it your best shot. Okay, so if you reduce this, then, which you can probably guess that you were going to do, then what we get is this reduced echelon matrix right here. All right, and so what is this telling us? Well, we have two pivots, so somehow these are related to the column space. And let's see if we can figure out how they're related. So let's take a look at this third column and see what it's telling me. Well, what that blue piece is telling me right there, if I call these columns V1, V2, V3, and V4, is this on the right here in the blue box is telling me that V3 should be equal to -3 times V1 minus 5 times V2. All right. Let's see if that's right. Well, -3 times V1 is V1 minus 5 times V2. All right, so pretty clearly that's -3, -5, and so it's -9. Sorry, this is a -2. -9 plus 10 is 1, which is V3. So this is telling me that V3 is a linear combination of V1 and V2, so that means that we don't need it in the span. Well, we can also, what is this other box telling us over here? This far box is telling me that V4 is equal to 2 times V1 plus 4 times V2. That's telling me I don't need the fourth column either. And so the column space, a basis for the column space, is the first vector, first column, and the second column. And so this leads us to the following observation about the column space. The pivot columns form a basis for call A. All right. Okay, so let's look at some theory questions for you to think about. So the first question I want you to think about is, suppose that we know that R4 is the span of 4 vectors. Do these vectors form a basis? Okay, and I'm going to give you another one to think about. Let's see, okay. So assume that the set S has n vectors in it, and S is linearly independent. And let's say these vectors are in Rn. Is S a basis for Rn? All right, so I want you to pause the video and think about whether these are, what the answer to these questions are. All right, let's talk about the first one. Do these 4 vectors form a basis for R4? Well, how do we think about this? Well, these vectors are all in R4, so we can create a 4x4 matrix. And we know they span R4. So what does that tell us about their pivots? Well, it tells us we must have a pivot in each row. These are the pivots. So I know I've circled them, but that's not really what I want to do. I want to put little stars in the matrix. So we don't know what these entries are in the matrix. So if we create a matrix whose columns are the vectors v1, v2, v3, and v4, we know that since the vectors span R4, we have a pivot in every row. Therefore, we must have a pivot in every column. And when you have a pivot in every column, they're linearly independent. And so therefore, yes, this is a basis. Let's look at the question below. We have the vectors v1 through vn, and they're linearly independent. So this tells us that there's a pivot in each column. And since you have n vectors in Rn, this tells us there's a pivot in every row. Which tells us that the span of S is Rn. Therefore, they must be a basis. All right. Last but not least, I want you to do a problem in a similar fashion to the one we did before. So this problem is looking at the functions sine of t and sine of 2t. Is this a linearly independent set? So I want you to do that using the techniques that we saw earlier this lecture. So work out that problem and then submit your notes. Let me know if you have any questions, and I will see you all on Thursday.